Last class we were discussing about the Euler and the Lagrange description, and then we moved on to the material derivative. Just to give a quick review, the Euler description is based on a fixed location. That is, if this is a road and different vehicles A, B, C are passing on this road, and you're standing beside this road here, having a speed measurement camera. So whenever a vehicle passes this point, you measure its speed. This is called the Euler description. This is the Euler way of measuring the speed. While in Lagrange approach, you are sitting inside any of these vehicles, let's say the vehicle A, and you note the readings on the speedometer of the vehicle at every time instant. That's every 5 seconds, 6 seconds. So you know the path of this vehicle as well as the speed. So the two descriptions are interrelatable, and they can be related through a proper transfer function if you know a transfer function. And then we moved on to the material derivative. We know that in Euler description, the velocity field is the most important field, right? And we know that velocity vector is defined as V equals to U I plus small v j. Capital V is the velocity field and U, V, W are its components along x, y, z direction. And we know that this velocity is function of x, y, z and time, right?
Yes, sir.
And each of these subcomponents u, v and w is also function of x, y, z and time. Each u, v and w is function of x, y, z and time, right? This u is function of x, y, z and time. This v is function of x, y, z and time, and is w is function of x, y, z and time. Clear?
Yes, sir. Yes, sir.
So if I ask you to calculate the acceleration, what will you do? You will say, okay, ji, take derivative of velocity field. I ask you to calculate the acceleration field. What you will say to me? You will say, okay, sir, take derivative of the velocity field with respect to the time. You will get the acceleration, right? इसी तरह होगा जी. Will it be so?
Yes, sir.
So the acceleration is derivative of velocity field with respect to time. But what happens now? This velocity is function of x, y, z and time. So firstly, we should take derivative of v with respect to time, the capital V, the velocity field. Then according to the chain rule, we should be taking derivative of velocity u, which is the subcomponent, with respect to x,
X.
and then the derivative of x with respect to time, right? Sorry, this would be velocity, not u. This would be capital V, the velocity field itself, the velocity field v, right?
Yes, sir.
Then you will take the derivative of the velocity field with respect to y, and since y is also dependent on time, so you will take its derivative with respect to time. This is your j component, and similarly the derivative of velocity field with respect to z, and then the derivative of z with respect to time. This would be k component. Clear? So this x by t is u component of the velocity. This y with respect to t is small v component of the velocity, and this is the w component of the velocity. Clear? So the acceleration is dv by dt partial v by partial t plus u partial v by partial x plus v partial v by partial y, and then w partial v by partial z. There will be I component here, j component here, and the w component, k component here. Clear?
Yes, sir.
Now we see that the derivative of the velocity is not that much simple. It is depending on the temporal as well as the spatial components. It is depending on the time as well as the space coordinates. So it is called the total derivative. And the total derivative, so we should have taken the total derivative of the velocity field, which is represented by A equals to d capital by dt. So capital by capital dt means you are taking the total derivative, the derivative with respect to the time as well as the space components, x, y, z, spatial coordinates. Clear? So this is the total derivative and this is its result. This is the result of the total derivative. This is the result of the total derivative. Clear?
Yes, sir.
There is some further detail into it. I should be writing that for discussing. Now, if I want you to calculate the x component of the acceleration, what you will do? This is the velocity field equation in front of you, and I ask you to tell me the x component.
सर फिर हम विद रिस्पेक्ट टू एक्स से करेंगे.
No, you will replace this v by this velocity field vector, the one I'm underlining with green color. This v in all the equation by u. Okay. So ax would be partial v by partial t plus u partial u by partial x I.
सर आपने शुरू वाले में डी यू पार्शियल यू नहीं किया, उसमें पार्शियल वी लिखा है.
यहाँ पे partial u by partial t plus v partial u by partial y, and then w partial v by partial u by partial z. Clear? इसी तरह जब आपसे कहा जाएगा कि आपने y कंपोनेंट कैलकुलेट करना है तो v की जगह आप small v रिप्लेस करेंगे. Similarly, if you want to calculate the z component, you will replace capital V with w. Okay?
Yes, sir. Clear.
Yes, sir.
So ax is partial u by partial t plus u partial u by partial x plus v partial u by partial y plus w partial u by partial z. Ay is partial v by partial t plus u partial v by partial x, v partial v by partial y plus w partial v by partial z, and similarly is the az. So this is called the material derivative. This description is called the material derivative description. So for any, this can be done for any property, not only for velocity, but for the temperature. If I ask you to calculate the total derivative for temperature, dt by dt, so you will just write. So this is the description of the material derivative, d by dt of temperature. This is the description for the material derivative, right? So you will have partial by partial t of that property plus u partial by partial x of that property plus v partial by partial t of y of that property plus w partial by partial z of that property. Now, if you want to calculate, if you have temperature field, you can calculate the total derivative for temperature field. You will just place temperature here in all the brackets, the temperature field. If you have pressure field, you can write pressure instead of T everywhere. Okay, is it clear? Is it clear?
Yes, sir. Clear.
Yes, sir.
So the material derivative for the properties of fluid for temperature, pressure. But we can see that the material derivative is keeping the velocity components u, v, and w. That's why velocity is very important property for any fluid flow. If you want to calculate temperature gradient or total derivative for temperature, you will need velocity. If you want to calculate total derivative for pressure, you will need velocity. So velocity is very important property in fluid flow. Now, what's the meaning of these terms? What is meant by partial t, and what is meant by this partial by partial x, partial by partial y, and partial by partial? Basically, material derivative is defining two types of terms in front of you. One that is dependent on time, one that is being derived with respect to time, and the other one is with respect to the spatial coordinates x, y, and z. So these are the two basic terms in the material derivative. If we take it there. So if we inspect closely, basically this total derivative has two terms. One is this term, which is dependent on the time. It is called the local term or the convective term, and this is the second term, which is called the spatial contribution. This first term is called the local or convective contribution, and the second term is called the spatial contribution. Clear? The local or the convective contribution is explaining the change in the property with respect to time, the Lagrange description, right? कि time के साथ क्या हो रहा है? What is happening with respect to time? And the spatial contribution is defining the change in the property with respect to the change in location, the islet description. Clear? Is it clear?
Yes, sir. Yes, sir.
So if the flow is steady, what will happen to the local or the convective term?
Zero हो जाएगी.
Yes, for steady state flows, the local or the convective contribution will be constant. There will be no change in the property with respect to time. So the convective term will become zero. So partial by partial t is also called unsteady contribution. the time rate of change of the property of a particle at one location is not equal to 0. And the other contribution is called the spatial contribution. We discuss it with the help of two examples. Consider water from a header tank. Let's say this is a header tank and the water is flowing in this tank. The cross section of this pipe is fixed. That is that there will be no change in velocity with respect to flow with respect to change in length. So if I write the acceleration field for this, because there is no change in velocity along the length, that is with change in x, y and z, there is no change in velocity, which means that velocity is constant with respect to x, velocity is constant with respect to y, velocity is constant with respect to z, right? So if it's constant, these terms will be 0. The spatial contribution will be 0. Is it clear?
सर ये विद रिस्पेक्ट टू टाइम भी जीरो होगा या फिर
Now let me draw it here.
सर ये पार्शियल v और पार्शियल t जो है
This is a header tank. Let's say this is a tank and this is a opening in this tank like this of, and this opening is like this. A fixed diameter pipe is coming from it. But let's say हम straight ही draw कर लेते हैं. Okay. Okay. The water will start flowing in this tank in pipe, right?
Yes, sir.
ऐसे ही. Initially, the velocity will be high. The velocity will be high. Why? Because there is a large amount of water. That there is a large amount of head in water, so that will give us greater velocity. But that velocity will be fixed at all points along this pipe. That will be constant throughout this pipe, right?
Yes, sir.
So it means there is no change in velocity with respect to location, with respect to spatial coordinates. But as the time passes, this level will drop, right?
Yes, sir.
With drop in this level, the velocity of the water will decrease because the liquid level is decreasing.
Yes,
Is
sir.
it clear? So the velocity is changing with time, but at all these locations, it is remaining fixed. Clear?
सही है सर, समझ आ गया.
So as the level will decrease, the velocity will decrease. So that level is decreasing with time. But along this pipe, that velocity will remain fixed. So there is no change in velocity with respect to the spatial component, but there is change in velocity with respect to time. So the acceleration will depend only on the temporal component or the convective term.
सर ये फिर हॉरिजॉन्टल या हॉरिजॉन्टल कंपोनेंट के केसेस में ऐसा ही है या फिर जो भी शेप आ जाए?
जो आपके सामने पाइप बना हुआ है जिसमें प्रोवाइड
सर
कि
लेकिन
उसका एरिया फिक्स.
अगर ये पाइप को देखा जाए तो ये मतलब एक डाउनवर्ड पॉइंट में तो इसकी वैसे हाई नहीं होनी चाहिए, मतलब वो जो फ्लूइड की स्पीड है ये तो हॉरिजॉन्टल की तरह ठीक है.
is decreasing. For the horizontal component it's fine, but we are talking about a specific component of the velocity. ठीक है? The overall velocity will remain constant. We are not talking about the free fall. You are talking about the acceleration due to gravity. We are not talking about that. Okay.
Okay, sir.
The velocity will remain fixed, but the acceleration due to gravity will increase. Okay, the fluid will accelerate, but with a change in time, not with change in location. Okay.
Yes, sir.
So the only term is the local. This acceleration is called the local acceleration, and the derivative is called the local derivative, or the convective acceleration, or the convective term, or the temporal acceleration, or the unsteady acceleration. These are all the name for this type of acceleration. Okay.
Yes, sir.
Then we consider another example. This is a common example. Let's say you have a water geyser. Let me. discuss the convective and the spatial. So in this water geyser, there's a cold inlet. There is a cold inlet, and then there is a heating coil in this geyser, and then there is a hot outlet. The outlet temperature is greater than the inlet temperature. So what's happening? Is the temperature changing with respect to time? Can you answer this question? Is the temperature changing with respect to time?
Yes, sir.
If I measure temperature at this point, let's say the inlet, at 0 second, at 10 second, at 20 second, at 30 second, will the temperature change?
No, sir.
If I measure the temperature at this
सर
point,
लोकेशन पे डिपेंड कर रहा है सर.
let me complete, let me finish. If the temperature is measured at this location at the hot end every 10 seconds, will there be a change in temperature?
No, sir.
No, sir.
No, sir.
If I measure the temperature every 10 seconds at this center line, will there be a change in temperature?
No, sir.
No, sir.
So the temperature is not varying with time, right?
Yes, sir.
But if I measure temperature at inlet, at outlet, at the center line, there is a change in temperature. But that change is due to change in location.
Position. Location, yes, sir.
So at this time, the temperature is dependent on the spatial components only,
Spatial
not the
contribution.
convective term. So the temperature field is steady flow. So it means that the flow is, or the temperature change is steady. There is no change with respect to time, but there is only change into the space. So total derivative is rate at which t changes with position and how quickly water changes position. That is partial t by partial s into us. The spatial part of the real derivative is also called the convective derivative. The temporal part is called the local derivative and the spatial part is called the convective derivative. So what does the convective part represent? It represents the change in flow properties associated with the movement of a particle from one point to another point in space. Clear? So how quickly, what is the location, how the location is changing and how quickly the location is changing. The velocity component with that is explaining how quickly that location is changing. Is it clear?
Yes,
सर ये
sir.
स्पेशल पार्ट्स बता दें कौन से पार्ट्स हैं लोकेशन.
Spatial parts basically the x, y and z components of the derivative, of the total derivative.
सर ये जो फिगर में है, फिगर में तो कोई नहीं है सर.
यहाँ पे
तो कोई नहीं है इस तरह.
यहाँ पे बेसिकली हो क्या रहा है? You define location here. Let's say इसमें location किस तरह की होगी? दो तरह की location होगी, x and y, right? It will be a two-dimensional flow. Let's say x, y.
जी सर, सही है.
There will be change in x direction like this, and when you move up, there will be change in y direction. Then there is again change in x direction. Then there is change in y direction. Then change in x direction, change in direction, change in x direction, change in y, and again x, and at the end y. Clear?
Yes, sir.
So the spatial part is called the convective part, and it explains how quickly, because there is velocity associated with it. If I add temperature here, so it will be explaining how the temperature is changing with respect to x and how quickly that location is changing. The u is defining the quickness or the steadfastness of that location. Now we solve an example in order to have more clear understanding of the material derivative or the convective and the spatial parts. So in this example, we have an inset incompressible flow past a sphere of radius r as shown in figure. There is a sphere of radius r, and there is a flow velocity v naught flow is approaching this ball, this sphere, and we're interested in calculating the given this velocity along the streamline. You are required to calculate the acceleration. Can you do that?
सर इसको खाली हम with respect to x ही करेंगे
Because v is only
I के साथ डिपेंडेंट है वो I component है
you will need to solve it like this. Just take me to the solver screen. So first I would recommend you to write the acceleration derivative for this. That would be equal to partial v by partial t plus u partial by partial x plus v partial v by partial y plus w partial v by partial z, right? If we see the velocity function given to us, this velocity function, this component is only u component, right? It's a one-dimensional flow. There's only one flow direction. So which means we will only have x component, right? Ax of the acceleration. There will be no ay, there will be no az. So here we will replace v by this v. This v will be replaced by u because there is no, this v component is 0, right? This w component is 0, which means this whole term would change to 0 and this whole term would change to 0. So ax would be equal to partial v by partial t plus v partial u by, u partial u by partial x. Is there any time component in this function? In the given function, is there any time dependent term?
No, sir.
Which means partial v by partial t would also be
0.
So the only term left is ax equal to u partial u by partial x. So u is given to us and we need to calculate partial u by partial x. Can we calculate partial u by x? That would be v naught. Derivative of 1 with respect to x would be 0 plus r cube. Derivative of x cube, 1 over x cube would be minus 3 divided by x4, right?
Over x4.
So
Yes.
ax would be v naught into 1 plus r cube by x cube multiply by v naught. So I will write it as v naught square into r cube by x4 and here we'll write -3. Clear? So this is the acceleration for this flow. Is it clear?
Yes, sir. Yes, sir. Clear.
So this is the concept we have already said, that streamlines are tangent to the velocity fields. We'll just solve an example to see that, okay, how we can, with the help of the streamlines, we can calculate the velocity field, or by using the velocity field, how we can get the equation for a streamline. Okay. So in this problem, you are given the x and y component. The x and y components of velocity for a two-dimensional flow are u equals to 6y feet per second and v equals to 3 feet per second, where y is in feet. You are required to determine the equation for the streamlines. We know that dy by dx equals to v by u or u by v. V by u, okay?
U.
We know v, we know u. We are required to determine the equation for the streamline, that is y as a function of x. So what we'll do, we'll write dy by dx. We'll put the value of v and u. The value of v is given to us as 3 and the value of u is given to us as 6y. We'll separate the variables. We'll write 6y dy equal to 3 times dx, right? Or you can further simplify, like 3 1s are 1 and 3 2s are 6 here. So we'll have 2y dy equal to 1 times dx. We will integrate both sides. So we'll have y square by 2 multiplied by this 2 equals to x plus constant of integration. 2 1s are, so y square equals to x plus c. Clear? This is the equation for the streamline. If we know this equation, we can draw streamlines for the flow, having the velocity field as 6y feet per second and 3 feet per second. Is it clear? In order to calculate c, we need to have 2 points. We need to know the value of x and y, or we can just put 2 coordinates. Let's say at x equals to 0, y equals to 0. So c is
0.
0. So in that case, we'll have equation x equals to y square. So what sort of streamlines we'll have?
Curve.
किस तरह का कर्व होगा अगर मैं कोऑर्डिनेट एक्सिस बनाऊं? ये अगर xy एक्सिस है, if these are the xy axes, for each y will have positive and negative value of the x, right? For x equals to 1, y would be 1.
1.
For x equals to -1, y would be, sorry, for y equals to -1, x would be
1.
1.
So it would be curved like this, right?
Yes, sir.
If c is 1, then we will have a curve like, let's say the equation is x plus 1 equal to y square. So it means that at x equals to 0, y equals to
1.
1. So the curve would be shifting, right?
Yes, sir.
So we'll have a curve like this here. So there will be a flow like this type of flow, and further streamlines you can draw. So the flow would be like this. Clear? So now you are able to draw streamlines for this flow. Is it clear?
Yes, sir.
So we solve another example to further show that the streamlines for a flow whose velocity components are u equal to c into x square minus y square and v equals to minus 2 cxy, where c is a constant, are given by the equation x square y minus y cube by 3 equals to constant. You are given the velocity components and you are required to calculate the equation for the streamlines. So you will do that simply again using the same understanding that dy by dx equals to v by u. You are given v, you are given u. You will just simply prove this equation, or in other words you can use this equation to calculate dy by dx. अगर आपने u calculate करना हो तो आप क्या करेंगे? If you want to calculate u from this equation, you will integrate it with respect to
U.
with respect to x, d by dx of this equation. तो अगर ये u के equivalent आ जाता है, this will be your equation for streamline having the velocity component u, right? So the constant is, derivative of constant is 0. Here you apply d by dx on this. You will have 2xy. Since y is a constant, so there will be
0.
0, which means that 2xy equal to 0, which means either x is 0, either y is 0, right? Similarly, if you derivate with respect to y, you will get another point that will explain, okay, if I derivate with respect to y, because the question is asking at which points the flow is parallel to the y-axis. So how can you tell that? Can you tell that at which points the flow will be parallel to the y-axis?
इक्वेशन सर वो x is equals to something होगी तो फिर पैरेलल होगा y axis के.
Being parallel to the y-axis means that x is fixed, right?
Yes sir.
Because if I draw the coordinate, x is like this. In order to be parallel to the y-axis, x should be 0, x could be, all these lines are parallel to y-axis, right? So at different values of x, the flow would be parallel to x-axis, y-axis, sorry, right? All these lines are parallel to y-axis. So the value of y is changing, but the value of x is fixed.
Yes sir.
So using this concept of dy by dx equals to v by u, we calculate first the equation of the streamline. In order to prove that, okay, the velocity components given are actually the velocity component of this equation. The answer is already given to us because it is saying that using these components show that this is the equation for the streamline. So we'll simply write dy by dx equals to v by u. V is minus 2cxy and u is c into x square minus y square. So the c will cancel out with this c and you will have minus 2xy divided by x square minus y square. Now, is it possible to separate the variables?
Yes sir.
कैसे separate होंगे?
सर मल्टीप्लाई कर देंगे क्रॉस.
But there is variables cannot be separated. So if variables cannot be separated, how do you integrate? Write down this equation.
Substitution से सर कर सकते हैं.
Write down this equation in front of you in a paper and how can you solve this? You should get from this equation. You have two options now. You can use this equation to prove that these are the velocity components. Okay, from this equation. How can you do that? Or in reverse, you can prove that from this equation, you get the equation for the streamline and you show that this equation is actually this equation. Okay. So we'll start from this point in the next class. Any question in today's lecture?